So now we're going to be looking at some more oscillation with pendulums. Okay, so the formula for period for a pendulum is 2 pi square root of L over G. This is the period equation we're going to use. Yeah, and so the length of a pendulum is a period. What is the length of a pendulum is a period of 0.5 seconds. So typically you know G, because if you're on Earth or something like that, then it's pretty clear. So if the period is 0.5 seconds, I can solve for L. So I'm going to do T over 2 pi squared would equal L over G, because the square gets rid of the square root. And so L is equal to G T over 2 pi squared. This is 9.8 times T, which is 0.5 seconds divided by 2 pi squared. It's equal to 0.062 meters. A pendulum has a period of 3 seconds and is located where the acceleration due to gravity is 3.79 meters per second squared. And it's moved to a location where the acceleration due to gravity is 9.82, so a slight change, because there is slight variation in gravity due to different heights from the center of the Earth, different altitudes. What is its new period? So initially, you kind of need to know the L over G part, but what we're going to do is we're going to do sort of as ratios here. So G is going to go from 9.79 up and increase up to 9.82. Now that's a factor. Like if I were to do the ratio of the different gravities, the 9.82 divided by 9.79, that would be a ratio of 1.003064 or something like that. Okay, so if it increases by that, my T is going to decrease by that amount, square rooted, decreases by the square root of 1.003064. So T2 over T1 would be 1 over the square root of 1.003064. And so T2 would just be T1 divided by the square root of 1.003064. That's how we deal with ratios. And it's really useful, not just for physics, it's really useful to be able to do it. So it's 3 divided by the square root of that answer. And that equals 2.9954 seconds. Okay. So very, very slight change, but a change nonetheless. Explain why so many digits are needed to value the period based on the relationship between period and acceleration due to gravity. Oh, well, because you're doing the square root of a small number, so it's an even smaller number. So this change is already up to 3 or 4 decimal places. Whereas the difference in G was maybe 2 decimal places, but when you do a square root of that, it ends up being like 4 decimal places or so. So, what is the effect of a period on a pendulum if you double its length? Well, for A, the period goes up. If I double L, then it will go up, but it will go up by a factor of root 2. What is the effect of the period pendulum if you decrease its length by 5%? So decreasing the length by 5% is saying the new length is 0.95 L, right? That's a decrease of 5%. And so T will decrease by a factor of 0.95, root of 0.95, because the L is under the radical here. If I plugged in 0.95 here, I'd take this would be root 0.95. At what rate will a pendulum clock run on the moon if the acceleration due to gravity is 1.63 meters per second square if it keeps time accurately on Earth? That is, find the time it takes for the clock's hour hand to make 1 revolution on the moon. Oh, okay. So if the period of a pendulum on Earth was 2 pi root L over G, and suppose that we make L such that in hours. Okay, so say we're going to make L such that T is 1 hour. Okay, on Earth at a G of 9.8 meters per second squared. I could calculate the L of that, so that's one way I could do it, and then just plug in a different G. But really, G is going to go from here to here. So my ratio of G1 to G2 is 1.63 divided by 9.8. And that is 0.1663. That's that ratio here. So g is going to decrease. That means t is going to increase, right? Because if g gets smaller, I'm dividing by a smaller number, so this whole thing is bigger, and this is t is bigger. But t gets bigger by dividing by the square root of 0.1663. Because if this sort of decreases by a factor x, this is gonna, or increases by a factor s, this is gonna decrease or divide by root x. So I'm gonna do 1 hour divided by the square root of 0.1663. And that is 2.45 hours. So that's how much slower it's going to run. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.